Hello, hello, hi. So we're ready to start chapter 6, so that's good news. And also good news is you remember when we had a day in the middle of chapter 4 where I said this is the hardest day of the semester. Well, that was a day where we tried to understand hypothesis tests and understand the argument that's involved in hypothesis tests. Well, we're past that day. That means that we're on something of a downhill trend. Is that the sections in chapter 5 were comparatively easy. The sections in chapter 6 are in fact even easier. So what I want to point out to you is something before we start in on the material in chapter 6. So let me click over to my window here. Is that when you look at chapter 6, you'll see that the sections are divided into 3 different parts. You can't really see that very well, but it says 61D, 61CI, 61HT. You can guess what CI and HT stand for. The D stands for distribution. 62, a D, a CI, and an HT. 63, a D, a CI, and an HT. 64, a D, a C, and a D, a CI, and an HT. So that is to say that we're just going to get formulas, just formulas. No sort of tricky concepts to master here. Then the concepts are the tricky part. Folks don't tell me, oh, this formula is killing me, because you just put the numbers into the formula. So we're going to get formulas for all these parts and just simply apply them. So I don't want to give you the idea that it's all a cakewalk at this point, but I do want to give you the idea that the hard part is the day that I said is the hard part, and now it's going to get easier. In particular, if you flip the book, I got a little bookmarker here in my book so I can find it easily. If you flip the book to page, this says 478, 478, and so it's the end of chapter 6, and what you'll see there is gathered in one place are all the formulas. So bookmark this page. I mean, I have a little index card that I shove in there, but whatever it takes, bookmark, we're just simply going to refer. Today we're doing this formula and this formula. Every one of these formulas has some little twist that you have to be warned about. But basically, the confidence interval is p hat plus and minus z star times some formula for the standard error. And then the hypothesis test is p hat minus p naught. And then on the bottom is some formula for the standard error. And we just apply the same stuff we've been applying now for some weeks. So I think one of the good things about this course is that it's true there's a point where it's tricky. That's absolutely true, but it was a couple weeks ago. And now a person can say, okay, I can both reinforce what I'm already confident with, and also feel like, again, not coasting, but just doing the same thing repeatedly. So a person who is struggling can start to say, because they all go the same way. Okay, so that's one of the things I really like about this course. All right, so let me put this out of the way here, bring my piece of paper back, and bring back my slide. So the slide for today is about confidence intervals and hypothesis tests for proportion. So section 6.1, and then later this week we'll do section 6.2, and then you won't be surprised to hear that 6.3 and 6.4 follow in succession. Okay, so for proportions, if you're reading a homework question and it says proportion of this or that, and obviously we're going to go over a couple of questions, it says proportion of this or that, why we're in this section. Okay, so there are some formulas, and I'm just going to click on the screen to show all the formulas. Here they are. There are some formulas. There's the magic formula. Square root of, I don't know what to tell you. Sometimes people are like, but you got a calculator. It's not that bad. Square root of p times 1 minus p over n. And the whole p and 1 minus p thing is that suppose, for example, you have a 40% chance of success, then you must have a 60% chance of failure. So if p is 0.4, 1 minus p is 0.6, and that's why they always come in pairs here in this context. Okay, but so there's some talk here about about under what circumstances you can use a normal curve, but we're always going to use a normal curve because we're not going to cover the binomial stuff just because of the we're trying to pare back and make only the material that we feel is absolutely necessary. Okay, so again, We're going to do proportions in this section. I'm going to do a couple of examples, and the formulas are right here and on that page in the book, and you should bookmark that page. Okay. I'm gonna, oops, clicking in the wrong place. Gonna go on to the confidence interval formula and the hypothesis test formula, and these are on that page in the book. Again, I really somehow clip that page, put a paper clip in there, some kind of thing. So confidence intervals, just to start with one of the two. We understand now what a confidence interval is about. We have a good idea of what it says, just to reinforce that idea. So we don't have a third grade idea of probability. We don't think that if you flip a coin 100 times that you have to get 50 heads. You know, we're not children. We now have a mature understanding of what happens. That if you flip a coin 100 times, you are pretty sure to get pretty close. How sure and how close? Well, that's what the formula is about. How sure and how close. So we know we're used to doing things like 95% confidence intervals, so that's how sure. And how close? Well, here is the standard error, and you got to multiply it by something depending on the confidence level. If it's 90%, you multiply by one thing. If it's 95%, you multiply by another. Okay, so really understanding the concept that the point of a confidence interval is to tell you where the true value lies. In this case, where P lies, because it's proportions. To tell you where P lies, and we think that P is close to P hat. We think that P hat is close to P. We think the two are close together. How close? This close. How sure? Well, you put in different numbers for Z star, and that's how you get the different sures. Okay, so let me go back and do the confidence interval question. You see the hypothesis test formula on the bottom. I just put them on the same slide just to try to get them all in one place. Okay, so it says on the NSBI test, students is ranked as good if their score is at least 51. I made up NSBI. Just baloney. So we test a random sample of 36 students and report that the proportion in our sample with such a score as P hat is 0.53. Okay. So this is a score on a test. This is the proportion of our students who got that score or better. It says state a 95% confidence interval. Okay, so let me click over to the paper. I know everybody, oops, I clicked in the wrong place. I know that everybody feels good about confidence intervals, or at least it's my sense that people feel good about confidence intervals. Here's my pen. So I'll write down the formula and I'll remind you what the Z star is. So the formula that I'm copying from the previous slide or from that page is P hat plus and minus Z star times the square root of. Okay, and again, just to flip back, I'm pretending that I'm flipping back to the previous page. It says P hat times 1 minus P hat over N, and so then a person says, aha, it's P hat, 1 minus P hat over N. And of course, all of our quizzes, all of our work in the remainder of the semester is going to be open book and open notes. So if you have that page marked, you're in good shape. Okay, now I know that the slide is on the previous slide, but it wasn't so long ago. There were N equals 36 students. We reported a P hat of 0.53. And we want a 95% confidence interval. Okay. The only thing so there's an N, there's a P hat, I'm going to put it in just a second. The only thing that I want to remind a person about is the 95% confidence interval. So the 95% confidence interval determines what number you write in for Z star. So I'll remind a person that we had, I'll just write it down. We had some numbers, and the numbers go like this. That, so if you, confidence and Z star. If you want to be 90% confident, you put down one number. If you want to be 95% confident, you put down another number. If you want to be 99% confident, you put down still a third number. The book lists like 80%. We don't care about 80%. Nobody in the world ever wants to be 80% confident. So 90% confident, the number you write down is 1.645. 95% confident, the number is 1.960. And of course, a person remembers that earlier in the semester we just called it 2. When we were first learning confidence intervals, we rounded to 2 and called it good enough. For 99%, but now we're doing the exact number, in the 1.960. For 99% confident interval, it's 2.576. Okay? If I was you, I would find that page with the formula in the book. Where the heck is the number of that page again? 478. And write these down on that page, because what the heck, put it all in one place, makes it easy to find. Okay. Okay, so now all I got to do is drop the numbers that are here into that formula. I understand what the formula is. The dropping in never gives anybody any trouble. That's what I meant about chapter 6 being somehow like more of a downward curve. Okay, so here I go. Hope I do it right. So it's 0.53 plus and minus. 95% confidence interval calls for 1.960. 1.960 times the square root of 0.53. And 1 minus 0.53 is 0.47. Got to multiply them and put it over 36 students. And the rest is calculator job. I'll take out my calculator and punch it out, but everybody in the room could use a calculator, that's for sure. Okay, here's my calculator. I hope you can read the darn thing. Hope I can read the darn thing. The light is not so good. Okay, so I've got to take 0.53 times 0.47 equals, divide it by 36 equals, take the square root equals, and multiply times 1.960 equals. So 0.16. So I think I've got a confidence interval of 0.53 plus and minus 0.16. And in this class, I like to add and subtract, just a habit, but I think it's a good habit. So 0.53 plus 0.16 equals, gives me the other end, 0.69. And the low end, 0.53 minus 0.16. The low end is 0.37. 0.37. That's the answer. And if somebody is scratching their head about something, I don't want to make them feel bad. But I do think that for us, there was a lot of rigmarole about exactly what a confidence interval means. But this formula is very straightforward compared to the stuff that we've been doing. It seems to me, and that's been my experience. Folks don't seem to tell me that the confidence interval gives me trouble. What does the confidence interval say? What exactly is it that's between these two numbers? And the answer is, bring back my thing. There we go. The answer is that we test a random sample of 36 students, not the population. That if we tested the population, we think the number would be between those two ends. That is to say, we think P is in here. We are 95% confident. We're not children. We don't think you can be 100% confident. But we're 95% confident, meaning that if 100 of us did it, 95 of us would capture the true number. So we're 95% confident that the true number, if we tested not 36 students, but every student, lies in this interval. Okay, so our understanding of confidence interval means that we understand what the answers we got. Actually getting the answers, forgive me for saying it about 8 times, but actually getting the answers in this chapter is actually one of the easier things to do. So a person can, I hope, feel like they can breathe a little sigh of relief. I hope. Okay. A person who had been feeling in sort of chapter 4 with like, oh, this is starting to get away from me. Okay, but it's coming back now. So that's good. All right, hypothesis test. So we're going to test H naught. Of course, H naught always has an equal sign in it. We're testing H naught P equals P naught by calculating this value. So of course I'm going to go through a standard hypothesis test type of argument from the question that's on the previous slide. But we have to calculate it's P hat minus P naught. P naught times 1 minus P naught over N. Of course, the two of them look somewhat familiar, but anyway, this uses P naught instead of P hat. I mentioned every formula has some little quirk, but it's not that hard. All right, here we go to the previous slide, and I'm going to do, of course, a question on the piece of paper, and it says, is there strong evidence that more than half of our students are good? Is there strong evidence that more than half of our students, that if we tested everybody, not just 36, if we tested everybody, we'd be, more than half of them would be above, score above a 51. Okay? Okay, so let me bring back my piece of paper. So it seems to me that we have a null hypothesis and an alternative hypothesis. If I can remember what all the parts are, we have a null hypothesis and an alternative hypothesis, and we remember that as an argument between two people. The null hypothesis person thinks that the number is the nominal value. The alternative hypothesis person thinks that it's different than the nominal value. And in this case, the nominal value is 50%. So they're arguing, of course, they're not arguing about the sample number because you just calculate the sample number with a calculator. That's all there is to it. So they're arguing about the true number. So they're writing down p's. You always write an equal sign there, always. Over here, they're arguing about whether p is 50% or whether p is bigger than 50%. So I think I'm writing 0.50 is, if we took a census, would half of our student body get the required score, or would it be bigger than half of our student body if you took a census? Okay, so now we're going to go through the hypothesis test, and it always goes the same way. You always say, assume H naught is true. Always. Always. That's how an argument goes. You can't say assume I'm right and the other side's not going to be convinced. You have to say assume you're right and convince them that what they're trying to say is not really very believable. Then the distribution of samples. The distribution of p hats is some kind of, looks like a bell curve. It's centered at 0.5 because if we're assuming H naught is right, then the samples would be clustered around the true number. And the spreadedness is this formula that we saw. The spreadedness is square root of p naught times 1 minus p naught over n. And again, we're always doing open book, open notes. The formulas are available to you. They're on that one page. Don't panic about this formula. It's just right on the page. You drop the parts in. A person can flub up the dropping the parts in, of course, but it's not really all that hard. 0.5 times 0.5 equals, divide it by 36 equals, take the square root, equals. And I got 0.083, about 0.083. For us, 2 decimal places good enough. So the next step is our sample. So where is our sample? Trying to draw the same graph, not a very good graph drawer. Where is our sample? 0.53. Well, we're asking for the p-value. What's the chance of being 0.53 or more on that graph? 0.53 or more, so we have to calculate, oops, I'm run out of paper here. So we have to calculate how far out on this curve is 0.53. That's easy. The z-score is 0.53 minus 0.50. Remember, 0.50 is the middle. Divided by, I forgot already, 0.083, 0.083. So I'm figuring out how far out is 0.53 on this curve. I'd use that formula, because that's the formula you use with a normal curve. The central limit theorem says this is a normal curve. You use this formula to figure out how far out you are and to calculate it. So 0.53, so let me clear everything. 0.53, take away 0.50 equals, oh, it's not enough light, divided by 0.083 equals, and I got 0.36, 0.36. That's 36 standard deviation units. That's not even a whole standard deviation unit. So we're asking, is 0.53 so far out on the curve that the H naught people would say, I can't believe you got such a freakishly far out thing by accident. I think maybe I must be mistaken. This is not freakishly far out on the curve. This is perfectly everyday. We are going to find that the p-value, this shaded area, is not small. Instead, the p-value is going to be large. So we're going to say to the the H naught people are going to say to the HA people, we know once I figure out the number, the H naught people are going to say to the HA people, you haven't convinced me, you're going to have to do better. So that is, we will fail to reject. But while I'm here, I'm going to figure out what is the p-value associated with a z of 0.53. Stackey is going to figure it out. I'm not going to figure out anything. What is the p-value? That's a question mark right there. What is the shaded area associated with the number I got from my sample? It turns out to have a z-score of 0.36. Okay, so I'm going to ask Stackey. Let's see if I can dial up Stackey. I had it here somewhere. Oh, there it is. Okay, and I got to get rid of what I have here. Yes, okay. Okay, so now I'm on Stackey. Forgive me too much fiddling around. That's a normal curve because the central limit theorem tells me it's a normal curve. Stackey taking a little while these days, I noticed. Okay, I need to get from 0.53 on out. So the shaded area, the part I shaded with my pen, was a right tail. And I don't want 1.960, I want 0.53. 0.53. And the p-value is written by Stackey right there. It's just a hair below 30%, 0.298. So the p-value is nowhere near 5%. It's not 1%, it's not 3%, it's 30%. So this is not convincing at all. The H naught people are going to say this is a perfectly everyday sample. I think the possibility that the true number is 0.5 is perfectly possible. Oh, forgive me, I entered the wrong number. I entered 0.53. Oops. I need to say 0.36 for the z-score. I'm sorry. Sorry, I was distracted hitting too many buttons. But we come to the same conclusion. So 0.36, forgive me for the mistake. 0.53 was wrong. 0.36 is right. 0.36 is right, and it has a p-value of about 36%, 0.359. Okay, well, I'm glad I got it right. Now I gotta go back to the piece of paper. So the p-value is 0.359, 0.359. Okay, once I entered the right value. That's nowhere near less than 5 or 1 or whatever number I was looking for. What number was I looking for on my alpha? I used alpha equals 0.5. So the value I got here is nowhere near less than 0.5. So not less than alpha. Not less than alpha. So you fail to reject. H naught. H naught doesn't say, you were wrong, but H naught instead says you're going to have to come up with stronger evidence than this to convince me. All right, so maybe 0.60 or maybe 0.65 would be convincing evidence, but 0.53 is just simply not convincing evidence. This is perfectly possible everyday sample in the context of what's here. So H naught can sensibly continue to believe that the true value is 0.5, and a sample, this is just looks to H naught like just a sampling thing. Okay, so we got a p-value that's much bigger than alpha, so we failed to reject H naught. Okay, I asked you for homework, please. I asked you for homework to look at, again, it's written on assignments, in assignments _ stats in the files area. So you go to home and then files, and there it is. It's written on assignment _ stats. But anyway, there 6.1d skill builder 1 and 6.1 confidence interval skill builder skill builder 1. Oh, sorry, this was page 406. Skill builder 1 91, 93, and 97. And then in the hypothesis test, it's skill builder 1 53 and 55. So a couple of skill builder 1s, 93, 90, 91, 93, 97, and on page for 6.1d, just to help a person find it, it's on page 46. Okay, so of course I sent around the material. I'm urging folks, it seems to me having some conversations that some folks have told me that that they have not been trying the homework before they try the quiz. The point of the homework is to prepare you for the quiz. So if you're getting to the quiz and finding that some questions you're like, what does that question mean? Well, that's because the homework helped you to see what the question means. So I'm going to urge you to make sure that you do the homework. Okay. All right, very good. We'll see you, and I will, of course, send you a notice when the when the next quiz is up. Okay. Bye bye.